So let's have a look at the test. So what we do is this test. We are working in a vertical ocean slice. No density gradients, no density stratification. So essentially, we use a model like this. Just a vertical slice. Okay? And we decide to use a horizontal grid spacing of 5 meters and a length of the model domain of 500 meters, which means we have 100 grid points horizontal. And we decide to consider a 100-meter water depth, but resolved a vertical grid spacing 2 meters. So we have 50 vertical. And that's totally different to the shallow water equation, where you only had one layer, essentially, only one grid cell, if you like. Here we have 50 vertical grid points stacked on. All right, so what we also do is we use a wave pattern. A wave pattern here is just something that, like a sine function, changes the pressure, the dynamic pressure near the surface. Increase, decrease, increasing, like a sine. Like something that moves the sea level up. But here it's what you do is you change the surface pressure. And then we look at the resulting wave. So just one comment. How do you choose grid spacing and size of the model domain? Is you sort of have to estimate what is actually the wavelength that you get. And what you do is that the total length of your model domain has to be several times the wavelength, so that there is no interference by the boundaries. And on the other hand, the grid spacing that you choose, the horizontal, also here the vertical, has to be small compared to the length scale of your wave is 100 meters long. You need something like a horizontal grid spacing of. Okay, here in this case you also have to satisfy the Cfl Stability Criteria. Okay, it's delta t has to be less than delta x divided by square root g. H and g times h is the maximum water depth. Okay, and let's have a look at the simulation of how does it look like.